Hello guys, this is going to be the Unit 2 review for ENGR 201. Sadly, since there is Memorial Day, I cannot have an SI session. So I'm making this video so that you all can review this as much as possible, and hopefully you can at least help each other out by looking at my solution, my explanation. But I will not answer questions over the weekend. Or at least I won't be able to quickly. So I really hope this helps. Just kind of give you an overview of what Unit 2 is about. This is where we really get into multivariable calculus. These are fundamental stuff you'll be using throughout the rest of calculus, DE, and probably a lot of other classes with the partial derivatives. And it's kind of just understanding what it means to hold certain variables constant. Other variables, consider them dependent or independent, and understanding how to do the algebra behind that. So if it doesn't make sense now, try really hard to understand as time goes on, because this will be very paramount when it comes to later units and later classes. I mean, I've used this in a lot of stuff so far, so you really try to understand this if you can. So I'm just going to get started. For this first problem, we have a function z that equals x plus y squared f of u, and u equals 2x squared y. So with this function f of u, we really don't know what it is. We have no understanding of what it is, but we know it consists of this variable u. So it's considered like a function of f of x and y. If you want, that helps understanding what it means. But essentially, you don't know what this f of u is. So whenever we do derivatives with it, we have to consider the derivative of fu, which is f prime. So partial of z with respect to x will equal, first off, we'll be holding y constant, since in this, and we take the derivative of all the x's, so it'll be 1 plus, so we hold y constant, so it's y squared, but we have this f of u here, so we have to take the derivative of f of u, so it's going to be y squared times the derivative of f of u, so f prime of u, and now we have to also multiply by the partial of u with respect to x. So the partial of u with respect to x, that would just equal 4xy. So then this answer would be 1 plus 4 times x times y cubed times f prime of u. Here, I'll show here partial of u with respect to x equals 4xy. Then I'll multiply that back in to the equation. So that's his chain rule right there, basic chain rule. Next problem, same thing, but just with y. So we take the partial x with respect to y, that's going to go to 0. Now plus, so we have y squared and f of u. So now we have two, I guess, functions that we need to be considerate of that we're taking the derivative of. So it's going to be a product rule. So we're the first one, it'll just be 2y times f of u plus y squared times the derivative of f of u, which we saw in the first one is f prime of u, times the partial of u, but instead with respect to y, and that will equal 2y f of u plus, here, we go ahead and solve for partial of u with respect to y, which will equal just 2x squared. Looks like a lambda there. There we go. So y squared times 2x squared, so it becomes 2y squared x squared f prime of u. Not too bad of a problem. All right. Next one, let's switch up the colors, go with green. So now we have a function of x and y that equals x cubed plus cosine xy plus x squared y cubed and equals 10. And y is defined as a function of f of x. So it's now it's asking us to find dy dx by taking d dx implicitly. So that pretty much just means that we have to take the derivative of the whole thing with respect to x. So that implies d dx of x cubed plus cosine xy plus x squared y cubed. That equals derivative of 10 with respect to x, it's just 0, so I'm just going to write 0. So this implies we're going to have 3x squared plus cosine xy, so cosine xy, it's going to, so it's going to be derivative of the inside times the derivative of the outside. So derivative of the inside, or sorry, the outside, we'll do that one first because that one's easier, is minus sine xy. Then I take the derivative of xy. So it's going to be a product rule. So where we have x will just be, when we take derivative of x, it'll just be y. Plus, when we do xy, we have to consider dy dx when we do this because, again, y is a function of x. So it would be x times dy dx, or I'm just going to write y prime. I prefer that, even though it can be easier to get lost, but it's just easier to write. Now, plus is going to be another product rule, which is going to be 2xy cubed plus x squared, sorry, 3x squared y squared. And this all equals 0. So now the big step here is to now get all my y primes to one side. Oh, for my y prime here. Is to get all of our y primes to one side so that we can pull it out and then divide by whatever is left over. So then we'll have 3x squared. Then we'll have minus y sine xy plus 2x y cubed equals, I'm going to subtract over, so everything I just brought over, I have on this side, these terms here with this y and this term. Then next thing I'm moving over is going to be this term with that negative sine xy in this term. So equal, so since I'm adding it to the other side, or I guess I'm subtracting it to the other side, it's become a positive sine xy. I'm going to put xy prime in front of it first. Xy prime sine xy. And then I'm going to subtract that 3x squared y prime. So now factor out these y primes. So now I have y prime times the rest of this, and I divide over what's left. I'm doing this for sake of space, so that applies y prime equals 3x squared minus y sine xy plus 2xy cubed all over what we have on the right side, which is going to be x sine xy minus 3x squared y squared. So that's all what y prime is, or dy dx, however which way you want to define it. Doesn't really matter. So this part A here, this should be nothing new for what you've done in the past. You probably have done this 1,000 times where you solve for dy dx implicitly. But now we're doing this to show that there's another way, an easier way, a Calc 3 way, by using the implicit function theorem, which can greatly reduce the amount of work you have to do and the amount of errors you might take to get to that work. So that theorem, I'm going to head right off to the side, and it's in our review here. Actually, I'll just show it to you in the review. Is dy dx equals negative fx fy, where, I'm going to write it down here as well. Fx fy is the partial of f with respect to x over the partial of f with respect to y. So back to the test. So then I want to do this in red. So that's why it says check your answer, because we know this should work. So fx, this is going to be 3x squared minus, so take derivative of x, so it'd be, so derivative of the inside, which would be y, because we're holding y constant and taking derivative of x, times sine of xy, and then take derivative of x holding y constant, so it'd be plus 2x y cubed. Fy would be 0, because there's no y's on the x cubed, because we're taking derivative with respect to y, or partial derivative with respect to y. Oh, it's going to be a minus. Be a minus x, since again now we're holding x constant. So we take the derivative of the inside of xy, y will go away, just leaving you with x. Then we times sine of xy. Now it'd be plus 3x squared, y squared. Now, if we're looking back at the review, it's going to be equal to negative fx over fy. Should be equal to negative fx over fy. So that equals negative, parentheses, 3x squared minus y sine xy plus 2x y cubed all over minus minus x sine x y plus 3x squared y squared. Now if you look over to our answer here, we have the exact same thing. The only difference is now is that we had our minus here at the top, so all I have to do is distribute it to the bottom, and we'll get the same thing. So then it'll equal 3x squared minus y sine of xy plus 2xy cubed all over x sine xy minus 3x squared y squared. And that's our answer. All right. Next problem is we have a function of x, y, and z, and equals y squared e to the 3z tangent 4x, and where each function x, y, and z equal their own function of t. We'll do some blue now. Now it's asking us to find the full derivative of df dt using the chain rule. It says do not use substitution, so it means don't plug in each of these in for your respective y, z, and x, then take the derivative. You want to use the chain rule to solve for it. So first off, a chain rule for this df dt equals fx times dx dt plus fy dy dt plus fz dz dt. So all we have to do is solve for each of these individually and then plug it all in. So I'm going to go ahead and do, see how I can organize this so where it's not a cluster. Let's try, I'll just start right here with fx. So fx is, of course, partial of f with respect to x. So here we have our tangent 4x. So there's going to be, and we're holding the y squared e to the 3z constant. So I'm going to write that down. Y squared e to the 3z, it's like our coefficient. Now times the inside of tangent, so be the 4x. Derivative of 4x with respect to x is 4. So I'll have 4 on the outside. Now times the derivative of tangent, and if you remember from Calc 2, which I hope you do, it's only been about a few weeks, derivative of tangent is secant squared. And then 4x. Now fy should be pretty easy. Derivative of y squared, which would be 2y, and then times everything else, which would be e 3z tangent 4x. Now fz, again pretty easy, equals 3, because that's the derivative of our exponent 3z with respect to z, should be 3 times y squared e to the 3z tangent of 4x. Alright, so we got our fx, fy, fz. Go ahead and mark it here. We got all 3 of these. Now we need dx, dy, dz. And so I could fit this on the bottom. I'm going to do it off to the side here. Do it in purple. Actually, I do it in green, so it's better contrast to the blue. I'm going to go ahead and change this so it's easier to look at as well. Let me make that green. Actually, make it red. And now I'll do this in green for dx, dy, dz in respect to dt. So dx, dt. So you just got to look at x. It is 3t cosine t. So derivative of 3t is 3. Derivative of cosine t would be minus sine t. Now derivative of y with respect to t, so you have t cubed plus 3 e to the 3t. So the first one's going to be equal to 3t squared plus 3e to the 3t. Now dz dt is t cubed plus natural log of t. So we have 3t squared again. Now plus a derivative of natural log of t, which is 1 over t. Alright, so now we have our dx, dt, dy, dt, and dz, dt. Now we can just plug it straight in. I'll go ahead and plug it in with purple. So we have the whole, all 4 of my colors at the top, except for black. I just don't like writing in black. Everything, all the questions are in black, and then I feel like it gets all mixed up into it. So it'd be df, dt. So I got to plug in fx 4 y squared e to the 3z secant squared 4x. So it's our fx. I'm going to put some brackets around it, make it more distinguishable, times dx dt 3 minus sine t Now plus fy, which is 2y e to the 3t, tangent 4x. Now dy dt, which is 3t squared plus 3e to 3t. Now I'm running out of space, so I'm going to write down here below. Plus fz, fc being 3y squared, e to 3t, tangent 4x. Close bracket, now times dz dt, which is 3t squared plus 1 over t. So this one isn't too bad of a problem. Big thing is to know this equation here, how do you deduce the chain rule, and how you solve for each individual component for it. And then all of that, and after that it's just plug and chug. Nothing else is really big or new, or I feel like you have to learn more. It's just you learn one small component and then you just apply everything you've learned in Calc 1 and 2 into this problem. You're not really learning new knowledge, just more tools. So not too bad of a problem. Now this next one, we have a function of u, v, and w. That equals the natural log of w plus cosine uv, where u equals a function of x and y, v equals a function of x and y, and w equals a function of x and y. Now it says find partial of f with respect to x using the chain rule. Do not sub for x, y, and z. So it's the same deal as the previous problem, but this is a little different. So the biggest difference between this problem and the last problem, we couldn't write. I wanted to note that on the last problem we wrote df dt, and we were able to do that because that was the only t was the only variable for each of the functions of each of the functions x, y, and z. But now u, v, and w, they're now functions of x and y, so that means that we have to do partials at this point. You're able to do a full derivative when there's only one variable in the function. But now there's two variables in each function, so we have to use partials. So I'm going to go ahead and write out the chain rule. I'll do it in the same colors as I did before. Partial of f with respect to x, and now it equals fu partial of u with respect to x plus fv partial of v with respect to x plus fw times the partial of w with respect to x. So hopefully this was a little bit easier than before, because it's a little bit extra work. Let's see, I did it in red last time for the f's. So let's see if I can get it to fit all up here. So f of u, so that's the derivative of this with respect to u, which should just be the natural log of w should go to 0. So I'm just taking derivative of cosine uv with respect to u, which will be negative v sine uv. Now I have to do f of fv. It's going to be the same thing as the previous one because it's pretty much the same function, but instead of v being my coefficient, it'll be my u, because now we're treating u as constant. Now f of w, and that'll just be the derivative of natural log of w with respect to w, because the other one's considered a constant, so it would go to 0. So we just have 1 over w. So not too bad, not too difficult. They definitely made this problem easier because you have like a fraction of the space, like at least half the space, maybe not even half. Now I gotta do partial of u with respect to x, partial of v with respect to x, and partial of w with respect to x. And I'll do that in green like I did in the previous one. So partial I'm going to start over here just in case it gets a little bit longer. So partial of u with respect to x equals 3x squared. So you have 3x squared plus 4y, so it just becomes 6x. So not, never mind. I thought these were going to be way longer, but they're not. Next one is v. The partial of v with respect to x. And that equals, so it's e to the x squared, so I have to do derivative of x squared, which is 2x, times e to the x squared. And then natural log of y just goes to 0 because it's considered a constant. So now I have to do partial of w with respect to x. And we have tangent inverse of xy. Ooh, that's a doozy. I don't know if I remember that one. I believe it's derivative of the inside still. So xy, so derivative of xy, which would be y, over, I think the derivative of tangent is 1 plus x squared. I could double check that. Or it would be 1 plus u squared. So it would be 1 plus x squared y squared. Check in the answer real quick. Oh, well, it's marked out. It doesn't fit on the sheet. I think it's 1 plus x squared y squared. Yeah, that looks right. All right. So now we have our f's, our partials for our u, v, and w with respect to x. We can now just plug in chug to our original equation, meaning df dx, or sorry, partial of f with respect to x equals be f of u, which is negative v sine uv times partial of u with respect to x, which is 6x, plus f of v, which is negative u sine uv times partial of v with respect to x, which is 2x e to the x squared, plus fw, which is 1 over w, times partial w with respect to x, which is y over 1 plus x squared y squared. Not too bad of a problem. It's pretty much the same as the last one. Remember, the only difference is the notation you use whenever you're doing functions of single variables or multivariables. So if you're taking derivative of a function that has independent variables dependent variables with multiple variables, in this case where we have u of xy, b of xy, and w of xy, then you have to use partials. But if you have sometimes in the previous problem, in number 9 on here, you can you can do full derivative if your functions of your dependent variables x, y, and z are of just a single variable like x of t, y of t, z of t. So go on to the next problem. Let's do red. All right, so now x, y, z plus y squared plus y z natural log of x equals 10 defines y as a function of x of z. Implicitly find dy dx using the implicit function theorem for partials. No credit for taking partial of x with respect to while holding z constant. So what this notation here means that I'm holding z constant. And that's important to note for this problem because we couldn't use the implicit function theorem if we had more than one variable that's considered an independent variable. we need to have one independent variable and one dependent variable. So here we have y, and we have x, and now since z is being held constant, this is basically a constant. It's not a variable anymore. So we have our dependent variable and our independent variable, x, y, then x. So then we're able to use the implicit function theorem. Another thing to note, and I didn't mention it on the earlier problem, we set this equal to 10. If you have any equation like this equal to a constant 10, we can then just say f of x, y, z equals that constant. In this case, 10. And if we can get a function to equal 10, then we just know that if we can get an equation, like if your variables of x, y, and z, or whatever they may be, to equal a constant, then we can say that function of these variables equals that constant. And it's what allows us to use this implicit function theorem, because right now, you look at it, there's no function in this. There's no f of x, y, z in this. Before, you were given an f of x, y, z that equals this, but now you're only just given an equation that equals a constant. So you need to know that f of x, y, z can be set equal to a constant for an equation, and then you're able to do math, such as like partial of f with respect to x or whatever, to solve for the problem, like we're going to do here. So we have partial of y with respect to x while holding z constant. Since once it's used as implicit function theorem, so that means it's going to be negative fx over fy. And that equals the partial of f with respect to x over the partial of f with respect to y times the negative. So partial of f with respect to x, that will be, so the first term, it will be yz plus y squared would go to 0 plus yz natural log of x, so it becomes yz over x. So that's our f of x. Now our f of y. So now we take the partial derivative with respect to y. The first term is going to become xz plus. Next one's going to be 2y. Next term will become z natural log of x. And then we have to always put our minus sign. You can leave it on the outside. You can distribute it. You can do whatever you want with it. It doesn't matter. It'll be mathematically equivalent. So this is all you really have to do. Just use the implicit function theorem. But you just need to understand these little concepts of what does it mean to hold, like what that notation means. It means holding a variable constant. And knowing that you can set a function equal to a constant and then evaluating it as if it were a function. Like whatever is on the other side is a function. All right. Moving on to the next one. I'm going to do purple. So now we have a function u, and that u is a function of w, x, y, and z. And that equals this equation here, cosine wy, wx squared yz, sine xz. Now with the constraint on u that wx squared wxy plus y squared equals 5. So what a constraint is kind of like a given domain. This is the only values, like all of your variables have to work together to equal this constant here. So that means that they all can't be independent of each other. Some of them are now dependent upon one another. You can have w and x be dependent upon y. You can have x and y dependent upon w or whatever. But you can't have all these variables, w, x, and y, be independent of each other. And this becomes really important later on in this problem. All right, so the first part A, asks us to find the partial of u with respect to x in general terms. So normally, sometimes they'll give you all of the terms that they wanted in. Sometimes they'll just say, like how I did on my worksheet, I'll show it to you. Right here. Find... Here. It says find in terms of fw, partial w with respect to y, etc. and they don't give you the rest of those variables. So sometimes you just need to know what they mean or what they're asking for. When sometimes they'll just give you just FW or FX, and it's like, oh, and so on. And in this case, they're being courteous and telling you what all does this function encompass. But don't rely on them to do on that for your test tomorrow. They might, or not tomorrow, Tuesday. They might do it for the first test, but I guarantee you they won't do it for the second test. So it's going to be partial of u with respect to x. And that equals, well, I'll go from w to z. So I have fw times the partial of w with respect to x plus fx. And the only reason why there's no partial of x with respect to x is because it's 1. That's it. You can write it down if you want, but the only reason why there's no chain rule for it is because it's just fx. Because when you have partial of x with respect to x, it's just 1. That's why whenever we do the partial implicitly of something, that's why we had that partial y with respect to x, because whenever time we do it with x, it just goes to 1. So we won't have to write it down ever. It just happens, and it's implied that it happens. You have fy partial of y with respect to x plus fz times the partial of z with respect to x. All right, so that's pretty. This is something that should be ingrained in your mind by now. It's in the review if you really need to look at it. I've given you a couple examples of what it looks like and what you need to do. So really understand how to do that. It's imperative. That'll be at least that's how you get like about half the points on this part of the test. All right. So now we're asked to find partial of u with respect to x. Looks like a k, but we have to hold y and z constant. I'm going to change it up to blue. So we have to hold y and z constant. And what that really means is that when we solve for our, I was writing equal sign. We solve for our partial of u with respect to x in general terms we did in the first problem, some things are going to go to 0. So if we're holding y and z constant, so fw will still be there. Partial of w with respect to x. Our fx will still be there. But now our fy is being multiplied by a partial of y with respect to x. If y is being held constant, then it's the derivative of a constant with respect to x. So this becomes 0. Same thing for fz. I'm holding z constant, so I'm taking the partial of a constant with respect to x, so it just goes to 0. So that I only really need to worry about partial of f with respect to w times the partial of w with respect to x in fx. So these are the only 3 things we need for this part of the problem. All right. So now we need to find that. So fw, we'll just go ahead and solve for them individually and then plug it in. So f of w. So we just look over up here to the top. Just take derivative everything with the w with respect to w, and if it doesn't have a w in it, then it goes to 0. So the first one, cosine wy. So that becomes negative, and since we're taking derivative of the inside, wy, y is being held constant, so we just take derivative of w, so we're left with y times sine of wy plus derivative of wx squared yz. We just take derivative of w, x squared yz is held constant, so it's just x squared yz. Then the sine xz considered constant, so it goes to 0. I'm not going to write that down. Now I have to find the partial. We'll solve for the partial with respect to x. Actually, never mind. We'll just do fx first. We'll do fx. So then fx, same deal. First term does not have an x in it, so the derivative of cosine wy with respect to x is 0. Next term we'll have 2w x y z. Now plus derivative of sine xz, so derivative of xz with respect to x is z, times derivative of sine, which is cosine xz. And now we have to find the partial of w with respect to x. So, and to solve for that, this is and kind of help make it more clear. This partial of w with respect to x is more like partial of w with respect to x holding y and z constant. It's kind of implied, but that's what we need to solve for. And we solve for that by using our constraint. The only way you can solve for a partial with when you're given, like if it's a variable with respect to another variable and it's on the inside of your function. So if I'm taking the partial of y with respect to w, the z with respect to x, and it's within the function, then I need to use an outside equation like the constraint. So I have to use the constraint, and there's two ways you can go about it. You can either use the implicit function theorem, because we are dealing with two variables and we're considering w as the dependent variable and x as the independent variable, and everything else is being considered constant. So we can use the implicit function theorem, or you can solve for it implicitly. It does not state either, but you can use either. And I'll just use the implicit function theorem because I think it's quick and easy. So like I said before, whenever you have something equal to a constant, we can say that, oh, that equals f of whatever. And since it has x, w, x, and y, it's going to be a function of w, x, and y. There's no z in it, so I don't need to include z if I really cared. Because it'd be wrong for me to include z in it, because now I'm saying, oh, u equals this, u equals that, and that's not true. U is constrained by this, but not the same. So to solve for it, so I have to remember, I'm going to have to say that f, I'm just going to say function f equals w squared x squared plus w xy plus y squared, which equals 5. Now, for me to solve for partial of w with respect to x, using implicit function theorem, then I would just be saying, oh, the partial of w with respect to x, holding y and z constant, equals fx, negative fx over fw. And remember, this is not the same as what I just solved here. This, not the same as this. These two things are not the same. You have to solve for this and with respect to the constraint. So take the partial derivative of this f with respect to x. So it becomes 2w squared x squared plus wy. Oh, sorry, that shouldn't be an x squared, it should be an x. So 2w squared x plus wy, the y squared goes to 0, over fw, which should be 2w x squared plus xy plus 0. So now we have all three of our components, fw, fx, and partial w is spread to x holding y and z constant. Now I can just plug that all in to this equation up here. I'll write it right here. So that means a partial of u with respect to x holding y and z constant equals fw, which is negative y sine wy plus x squared y z times partial w spread to x holding y and z constant, which is this big old mess here. Eraser stopped working. All right. And then we have, I'm not going to distribute the negative, I'm just going to leave it. 2w squared x plus wy over 2w x squared plus xy. Now plus fx, just 2w x, y, z plus z cosine xz. So this problem's not too bad. Remember, there's several different ways to solve for this component. But note that when you solve for it implicitly, these do not mean the same thing as these. These are not equal. I'll make that abundantly clear. But you can solve for that implicitly if you like. And it's the same deal as we do before. You just take the partial of everything with respect to x. And every time you take a partial of w, you have one of these symbols, the partial w with respect to x. All right, so this next one is really quick and easy. So it's saying, oh, never mind. The last one's really quick and easy. So this next one is pretty much pretty much the same as the previous one. The only difference is now instead of holding y constant, we're holding w constant. Z still being held constant. So go ahead, we'll write out what our general equation is that we're going to plug into for our thing. And instead of fw, we're now going to go straight into fx, I like to write it in order, plus fy times the partial of y with respect to x. Because now y is not being held constant anymore. All right. Now to solve for, let's see, might have to zoom out a little bit. Now I'm going to solve for fy and fx. So fx we still have from up here, so I don't need to solve for it again. So I don't have to solve for it again. So I'm just going to solve for fy, and I'll plug in fx in from the previous one. So fy would equal derivative cosine wy. So I'm going to have negative w sine y, wy, plus derivative of wx squared yz with respect to y. So I have wx squared z. Now plus, there's no y in that last term, so that goes to 0. That's our fy. Now we need to solve for our, I'll make this a little bit more specific, partial y with respect to x holding w and z constant. And again, we're going to use our constraint. You always have to solve for this term here, you always have to use your constraint. And again, we can do the same method as before. Partial of y this time. Of y with respect to x holding w and z constant equals the negative fx over fy. We already know our fx. Oh, sorry. This is why I said. That's why I said. Yeah, we do know our fx though. It's just right here at the top. So it equals negative 2 w squared x plus wy. So now fy we have to solve for. So this first term right here is going to go to 0. Next term we have wxy, so it becomes wx. Last term is y squared, so it comes plus 2y. We have everything. We can now just plug and chug. So partial of u with respect to x holding w and z constant equals fx. Remember, again, this from the previous one, the previous problem, just 2w xyz plus z cosine xz times, so not times, plus Fy, which you just solved for, is negative W sine Wy plus W x squared z. I want to make this a little bit smaller and move it back so I have more space on the page. I know OneNote goes on forever, but it bugs me if I go off the page. Now this is multiplied by our what we just solved for here, which is negative 2W squared x plus Wy over Wx plus, oh, that's a 2, not a z, 2y. So pretty much the same as the first, or I guess part B. C is the same as part B, just slightly different variable. Now the next one, this is where I was going to say, in this one, the constraint is crucial. So if you look at partial, so it says we're doing a partial view with respect to x, w, and y. Now I'm going to go ahead and write our constraint down here so I don't have to keep scrolling up. So it's w squared x squared plus, is it wxy? Yeah, wxy plus y squared. Equals 5. Let's make this purple. So this is our constraint. Now if you notice, in our constraint we have w, so we have x, we have w, and we have y. And all three of these, w, x, y, y. And this is important because this is what this is telling us, is that we're taking the partial view with respect to x, holding w and y constant. And so that means that when we really mean we're holding it constant, we really mean that we're holding it independent of our other variables. And so now we're saying, and since we're taking the partial view with respect to x is an independent variable. So we're saying that x, w, and y are all independent variables. Ignore that. W, x, and y are all independent variables. So if we have them all in this equation here, it's impossible. That means that they have to equal some finite number, and they're not variables anymore. They're just arbitrary constants, and that's not. No, that's not. It makes this like invalid. You can't solve for this. Because if I have w is independent of x, and x is independent of y, and w is independent of y, that means that they can just be whatever value they want to be without having to rely or depend on the other variable. Meaning that this necessarily, it won't equal 5 anymore. This no longer, it's impossible for x, w, and y to all be simultaneously independent of each other if they're all held to this constraint. So therefore, this is undefined or impossible, however which way you want to put it. Because x, w, and y cannot be simultaneously independent. Due to constraint. And you can write down what the constraint is, but this is kind of important understanding of what it really means to hold something constant. You're just saying that this is now independent of this. So when I take the derivative of something with respect to x, I just kind of ignore it because it doesn't rely on x. So and x doesn't rely on it. So why do I even need to bother with the independent variable It's kind of the same thing. When we hold something constant, we mean it's independent of it. Like how 5 is independent of whatever x is or whatever y is, whatever z is. It's just a constant. The same way that x, y, and w right here are saying that, oh, we're independent of each other. We can basically hold them as constants, but we can't do that for the sake of our equation up here and our constraint. All right, so I've gone over the whole test. I know I might have gone slow and explained each step a little bit more than I really had to, but I wanted to make sure that everyone understood exactly whatever I was doing, and I didn't lose anybody, because I sometimes can just skip 10,000 steps and end up in the answer and realize that I did not explain anything. So if you think I went slow or think I showed too much work, that's the reason why. I want to make sure that everyone can clearly understand what I'm trying to communicate. If you have any questions, please comment below, ask your classmates. I tried to make this so that it can be easily interpreted and you can kind of rely on each other to figure this out, because I'll be really hard to reach over Memorial Weekend. I'm going to be spending, I don't want to spend my time answering all these math questions. I love to help, but at the same time, I don't want to spend time just trying to help you all just because I can't have an SI session, answer all the questions just because I can't have an SI session on Monday. But if you do have questions, send them to me and I'll try to be responsive, but I can't guarantee anything. So learn to rely on your classmates and your friends. Anyone else that's older than you is also taking this class before, that do have the time. I hope you have a wonderful weekend and good luck on your test. Hope this helps.